Hello and welcome back. Today is the second day of the 5th week. So we were discussing about active mode locking. So very quick recap. So what we started with that active mode locking can be done using several things, and one of them is the acoustic devices. So what we said in the previous class is that this acoustic transducers, they can generate sound wave that can modulate the amplitude of the laser beam in the optical resonator. And we realized that since this acoustic device uses sound wave, and that plays a major role in modulating the amplitudes of the light wave, we need to understand the interaction between this sound and light wave. So we took an example of a glass of water and taking a acoustic transducer which sends the sound wave through the glass. So what will happen then, the sound wave will change the it will go through compression and dilation, and it will propagate through it. So if the transducer is here and the glass of water is here, then the wave will propagate downwards. And in the meantime, if you have a laser light, or any light for that matter, if it goes through the glass of water in this direction, then the frequencies of the light will also be shifted by some definite amounts. So we said that this effect is known as Debye-Sayers effect, and this Debye-Sayers effect is analogous to a diffraction, except for the fact that in case of light diffraction by a slit, does not change the frequency of light, okay, it just modulates the intensities. Now we raise a question here that, okay, fine, we understand that this is very much analogous to light diffraction by a slit, but then why do we have these frequencies like omega plus minus capital omega and omega plus minus capital 2 capital omega and so on. So we were here trying to answer this question. So what we did, we did a hypothetical experiment where we took an active medium which has a frequency refractive index value, say N1. So what we did, we took an active medium with a refractive index N1 which is higher than the refractive index of the environment, which is given as N0. So the environment refractive index is given by environment Ri is given by N0. Now I have an incident radiation which is coming with a frequency small omega. If N1 is greater than N0, then the light of the medium will travel slower. How much slower? Is N by N0 times slower. Why? That we already know. Knowing the relation between the frequency and velocity of light, we can say that, and how it is governed by the refractive index of light. Okay, most of the time we do not include the refractive index part in our equation, but to be correct, one must use the refractive index whenever you are talking about a propagation of light through any medium. Now if we can somehow modulate the refractive index of the medium N1, okay, so I can change it to N1, N1 prime, N1 double prime and so on by some way, okay, we do not know how, but if we can do that with a particular frequency, say capital omega, then that will cause the light in the medium to propagate either faster or slower, okay, because we have earlier said that due to this Debye-Sayers effect, if it takes place, then the incident frequency will be shifted by integer multiple of the frequency capital omega. Okay, in both the direction it can have downward shift as well as it can have upward shift. That means frequency can increase, decrease or increase. So the result is the modulation of the output light, and this output light is characterized by the frequency omega, small omega, and the side band frequencies which is governed by the capital omega. Okay. So we will have several frequencies appearing in the spectrum, and they will look something like this, which is on your screen. So the central part, this omega, is my incident frequency, and this frequency is being modulated by this amount, or in this side. Okay. So this is the upward shift, and these are the downward shift. These guys. So these are called sidebands because they were not there earlier. So this is my main band, that is also known as the carrier frequency, and these sidebands are created. Okay. So now just imagine at this point, if I can have this distance exactly same as the distance between two neighboring modes. When I talk about this distance, this is in frequency domain, all right. So if I can do this one, then this frequency, this particular frequency is nothing but the frequency of the next mode and next to next mode, and then so on. So this will create a situation, and this will happen for any given omega, right. So if I choose a omega anywhere, then the corresponding side bands will match to the neighboring modes. If I change the omega somewhere else, then again for that one also I will have this side bands which will match to the neighboring modes. So in other words, all the modes are now coupled, and they have a definite correlation with each other. And for the time being, if I just can say that if I somehow minimize these side bands, if I can say make huge losses to this side band. So if I can make huge losses of the side bands, then this will disappear, right. So this guy will disappear, and same will happen for these guys also. So only thing which will remain is this frequency, and that will be magnified because that will have the gain, and we know that when the gain becomes non-linear, then I will have a chance of laser output. And we already have learned that we can play with the width of the pulse, okay, that is created at this particular frequency by choosing the system which has say large number of modes within the spectral bandwidth. So in that case, I will have a selective pulse moving back and forth in the cavity, and that has a very short pulse width, and that is what our aim is. Okay. So there are a few important things to consider. Okay. The most important thing here is the length of this active medium. So in other words, the optical path through which the light is traveling, right. So it said that the longer the optical path, which we designate by L here in the material, meaning active medium, the greater are the amplitudes of the side bands at the frequencies omega plus n capital omega. So if my active medium length, so in the previous slide as we shown here, so if this is my L, and if L is longer, then what will happen? So here, if L is long, okay, so if L is long, the sideband intensities will grow. So, this will grow in intensity, right, if L is long. Now, if sideband grows, that means they are growing from something. So, what happens is they take this intensity from the carrier frequency. So, essentially this will go down. So, this will go down and these guys will go up, which is exactly the opposite of what we want, right. So, yeah, so here we mentioned it explicitly that sidebands amplification is reached at the expense of the amplitude of the fundamental beam at the carrier frequency omega, and that is what we do not want. So, the optical path length L is the parameter defining when device shears effect can occur. Okay. So, this involves a lot of detail. Right now we are not going into the detail of that one, but let us take it that this optical path length can control the occurrence of device shears effect. That means whether we will be able to create these side bands at a particular frequency gaps, which is defined by this omega plus minus n capital omega, alright. And then we can get a chance to have a proper mode locking if it fulfills the condition that this omega is equal to the delta nu, the gap between the two modes. Okay. Now, knowing this that this optical path length is very crucial, then we can have two different situations and then two limiting cases essentially. One is this one, where the optical path length is far less than the quantity given by capital lambda square by 2 pi lambda, and the other limiting case can be the optical path length is much greater than capital lambda square by 2 pi lambda. Okay. We are not bothered about how did we come to this conclusion because that is not a part of this particular course curriculum, but we will just look at these two values that can be obtained. So, in these two cases the capital lambda refers to the length of the acoustic wave and small lambda, as you know, is the optical wavelength. So, the first case, that is L much less than the right hand side, this particular relationship, it defines the critical length of the optical path for which this device shears effect can be observed. Okay. And this relationship also characterizes the conditions that is required for mode locking using acousto-optic devices. And just for your information, this is known as Raman-Nath regime, where optical path length is much less than lambda square by 2 pi small lambda, right. So, this particular relationship is of importance to us. Now, we should also know what the second relation mean for us. So, when the optical path length is much larger, it's not too difficult for you to understand at this point if you have understood the previous classes. If suppose the optical path length is such that it causes the shifting of the carrier frequency by certain amount, which is equal to the cavity round trip. Cavity round trip is quite large, correct? So, if it is that much, then what will happen? I can have a situation where I can select one pulse in the cavity and dump everything else, and essentially we can use it for cavity dumping. If you can if you look back the case where we did the cavity dumping, you will be able to relate this. Okay. Now, so all these things we came up to using the simple idea that okay, by any chance if we can modulate the refractive index and we did not know how to do that, right. But we assume that okay, there is something I can use that and modulate the refractive index of the medium, which we took as N1. So, how to do that? Okay. So, the simplest way to modulate the refractive index N1 is to make a periodic change of a medium's density, which can be achieved by passing acoustic wave, sound wave. Okay. Of course, you expected this one because we started with this acoustic devices. So, we are developing this, we are making a transition in a way like we know that acoustic device will be used. Now, how acoustic device will actually do the job of mode locking. So, we broke into separate parts, one where we show what acoustic device does, it sends sound wave. Now, again, if we need to modulate the frequency, what we need to do? We need to modulate the refractive index, and if I can modulate the refractive, what happens? Now, let us connect the acoustic device and this refractive index modulation. Okay. So, it is true that acoustic modulator can modulate the refractive index of the medium. Now, once it does, the acoustic wave creates regions of compression and dilation at the frequency capital omega. So, capital omega is the is the acoustic frequency. Okay. So, I showed you an image earlier, a picture like this, where we took this glass of water and then send the sound wave. So, sound wave propagates downward, right. Now, in actual acoustic devices, okay, the real acoustic devices, instead of this moving sound wave, they generate standing waves. Okay. So, they generate standing acoustic wave, which is totally different from this picture where this wave propagates downward. Okay. Now, if such standing wave is formed and if I vary the frequency, how does it look like? Okay. So, here we have given 5 different situations for the same type of column through which acoustic wave is being sent, and essentially that is forming the acoustic standing wave. So, we have given situations A to E. You can see that there are different modes are possible, okay, and A to E essentially covers from time 0 to the full period time, which is given by 1 upon omega. So, this okay. So, in these cases we have taken in different intervals, and you can see that the refractive index N1, refractive index of the active medium, at each place in this column, okay, at different times changes in a sinusoidal fashion with the acoustic wave frequency capital omega, right. So, if you choose any particular position of the column, say we have chosen this position, okay, which is given by this dashed line, okay. So, this is our selected position to look at this effect. So, if I select this one, what do I see? So, what I see is twice, that is in case of column B. So, these are little bit shifted. So, you can easily correlate, this refers to this one, okay. So, for B and D, the density, okay, is uniformly distributed over the column, okay. On the other hand, for case A and E, you have the maximum refractive index. Okay. So, these colors are essentially the intensity of this color is in the grayscale though is giving you the amount of refractive index or the value of the refractive index. So, darker it is, higher the value, and lighter it is, lower the value. So, if you look at along this line, the selected position, you will see that this is varying. So, it is darkest to a little faded, and then totally like it is giving nearly the lowest value, and then again it goes up. So, twice the maxima occurs. Okay. So, at these two places within a time period, and here it is the minima. Okay. So, this is the smallest at 1 by 2 omega, the value of refractive index N1 is lowest. So, thereby varying the omega, you can actually change the refractive index. Moreover, you can change it in a very systematic manner, in a periodic manner. Why? Because you can see that nature of the curve of N1 against this 1 upon N omega, that is essentially in terms of T, capital T, the period, is sinusoidal in nature, which is a periodic function, correct? So, remember just few minutes back we said that the requirement to get this mode locking is the creation of a periodic variation of the refractive index of the medium, so that I can modulate the light wave. All right. So, I have put this picture once again, so that we can see when we discuss. So, now we can see from this picture that twice during the cycle capital T, which I already mentioned, when the density is distributed uniformly, what will happen to the light wave? Nothing will happen to the light wave. The light wave will pass through unchanged. So, the outgoing light will have the same frequency as the incident one. So, if it starts with small omega, the output also will be small omega, and the amplitude will remain the same. So, no change when it is uniformly the refractive index is uniformly distributed. Now, at any other given time, what will happen? Will achieve diffraction. So, essentially de Baissier's effect, which will lead to the appearance of this additional side bands at omega plus minus capital omega, and this will happen at the expense of the weakening of the amplitude of the carrier wave at frequency small omega. We have already seen that, nothing new. So, this is the reason why an acoustoptic transducer modulates the amplitude of the light within an optical resonator. Okay. So, if this modulation can be held at a frequency equal to the difference between the longitudinal modes, which we defined in the previous class as small omega subscript q, which is equal to C by 2L. We have been dealing with this one for a long time, so we know this one. We will achieve de Baissier's effect. Not only de Baissier's effect will happen, but we will achieve the mode locking, and that is the condition. I should be able to vary the refractive index so that I can modulate the amplitude and create de Baissier's effect, so that the frequencies are shifted by certain amount, and if I can control this amount of shifting such that they are equal to the gap between two successive longitudinal modes of the cavity, I got mode locking. Okay. Now, how do you do that practically? So, you need to use an acoustic modulator. Okay. So, this acoustic modulator generally can be, as I said in one of the previous classes, it can be like fused silica, and this is one of the most used system. So, if you take a small prism of fused silica or small small window of fused silica and place it extremely close to the optical resonator mirror. Okay. Then what will happen, that is shown in the in this picture given here. So, the sound wave is given. So, this acoustic modulator is attached right here. So, this gives the sound wave, and this sound wave will modify the refractive index of the medium. Okay. So, depending on the frequency of the acoustic wave, you will create the de Bézier's effect, and for a definite frequency you will see this kind of thing where this guy is just omega and this is like omega plus omega, this is omega plus 2 omega and so on, and this is omega minus capital omega, omega minus 2 capital omega, and this is. So, by now you probably have understood what we are going to achieve. Now, they are being diffracted, correct? So, one beam which is unchanged in the frequency is falling here on the mirror. What will happen? This particular frequency small omega which we are selecting, okay, that will be amplified. So, we have written down here explicitly that the piezoelectric transducer at one of the end of a prism generates the acoustic wave at a frequency capital omega, and if I choose the frequency capital omega to be equal to c by 2L, where c is the velocity of light, L is the length of the cavity, the end walls of the prisms, it is a practical concern that the end wall of the prisms are polished to permit acoustic resonance, which is needed for practical reasons to produce the standing acoustic wave. Okay. A laser beam inside the optical resonator passes through the region of formation of the standing acoustic wave, as we shown in the previous slide, like this. So, this is my essentially the beam which is coming from the active medium, and that will interact with this standing acoustic wave. As a consequence of this interaction of the laser light coming from the active medium and the acoustic sound wave passing through that prism or glass plate made up of fused silica and attached to a acoustic modulator, the laser beam with the frequency omega is periodically modulated at the frequency this. We know that. So, this will happen at the expense of the side bands. Why? Because if you notice the previous picture here, so this guy is the axial guy because this is passing through this axis of the cavity. So, the cavity is formed in such a way that this beam is the axial beam, it goes into the along the axis of the cavity. So, only this axial beam participates in the laser action and other beams are not going into the cavity active medium back again. So, it will go out of the mirror. So, I will incur losses for the side bands, and that is what exactly we want. We want to lose the side bands and we want to amplify the axial band at small omega. So, the side bands which are deflected from the main axis will be suppressed, since the length of the optical path of the side bands is different from capital L. Of course, you have to follow the standing wave condition of the optical cavity, right. So, if these side bands are not supported by the cavity, then also I will have the losses. So, in that case, this axial beam will form the laser output, and this is one pulse because this has been chosen in such a way that the every round trip one light output will come out. Okay. Again it will go back and come back to this output coupler, one pulse is going out, and this pulse is extremely narrow. So, this is how the active mode locking involving the acoustic modulator is done. Now, traditionally the acoustic modulation is used in flash lump pumped solid state lasers such as Nd:YAG lasers. Any continuous wave laser can be actively mode locked, and that can produce a pulses in the having energy of few nanojoule, and it may have a repetition rate of say 100 to 250 megahertz at max. If someone needs more energy, what you need to do, you can select a pulse from the train and you can amplify it further by something called regenerative amplifier, which we are not going to discuss during this course. If someone is interested, you can go through the books that I have suggested. If you want to even further increase the power, you can combine a Q switching or cavity damping to this mode lock laser, and this cavity damping or Q switching that can give high power. So, if you can combine mode locked laser with a Q switching and cavity damping technique, you can end up getting higher energy output. So, we will stop here today, and in the following class we will start learning about other type of mode locking procedures. Thank you very much.